All right, well, I just gave back some homework. And today we do have a homework assignment due. So are there any questions? I think, let's see what we had you do. It was, these exercises for today are on existential quantification, right? I was looking them over before class. It seemed like they were all fairly straightforward. Does anybody have any question?
I have a question on the last one.
Sure. The last one being 9.28, Existential Introduction. So, oh, here it is, Existential Introduction. Did I give you a hint on that?
No.
You know, that Existential Introduction, it's kind of like the one that corresponds to that is, you know, with an implication with the universal. What is that one like?
It's the opposite.
Yeah, it's kind of like the instantiation, right? Now, you remember the heuristic that we said to use? Well, oops, going the wrong way. So this existential introduction is similar to that instantiation. Okay, do you actually have a specific question you want a hint?
More of a hint. I don't know if I should use 917 or if I should try to use a different theorem to get there, or if I just start with the left-hand side and say all
Well,
this one.
you gotta convert it into universal, right?
Yeah, I think the way to do this is to try to convert it into universal. But now the thing that's tricky about this, though, is that we have this implication, right? And so, okay, so I have a big hint. The big hint would be to start with the whole thing. And, well, no, I take it back. You don't have to start with the whole thing. Well, the big hint would be try proof by, well, before I give you the hint, yes, proof by contrapositive. Because if you do proof by contrapositive, it's the implication is the other way, and you have a not in front of the exists. But if you have a not in front of the exists, then you can use this generalized De Morgan.
But it's flipped
But I think I'm
with the negation over equivalence.
right. But I think that those negations will. I think you might have a double negation come in there. Are you with me? And I think it should fall right out. How's that? So the hint for that is to use proof by contrapositive. Everybody remembers what contrapositive? What's the contrapositive of P implies Q? Not Q implies not P. So to do proof by contrapositive here, what you would prove is you would prove that not the right-hand side implies not the left-hand side. Then I think you can start with not there exists and use instantiation. I think. Does that work? Has anyone done this?
Well, you have like the universal one implying the test of substitution. So because you have the not P.
Yeah. So I mean, do you have to use universal with P replaced by not P?
Well, couldn't you just say 913, which is 913 with P replaced by not P?
Oh, is that what you have? Is it that easy?
I
What is 913?
don't know if that's legal.
Well, I mean, anything.
Oh.
If you do the whole thing.
Because I did De Morgan's to be
Yeah.
proof by contrapositive, and so I have not. There's this an X.
Yeah, so if you do the whole thing, yeah.
Yeah.
Yeah. Oh, that's easy. Turns out,
So what does that give you? Just, that is 913 with the whole thing replaced by not the whole thing?
No.
no, I think it's with P replaced by not P.
Oh, that's it?
Yeah.
Oh, that was easy.
Easy for cheesy.
Okay, are we good? Okay. Yeah, and I think most of the other ones were to use that heuristic, you know, get the existential to be using one of the generalized De Morgans to be into a universal, and then use the corresponding property in the universal and then get it back. I'm pretty sure that those all work out. Did you, is that what you
The
found?
only one question I had was on, I switched it into the universal using 917, and then I had P and the universal quantification. Can you use 9.17 with P and the whole thing? Just switch it back. It was on 922.
Well, I mean, I don't quite understand your question. I mean, on 9.22, you have, you're talking about this side of 9.22?
Well, I started with the left-hand side, and I used 917.
Okay, are we trying to prove 922?
Yeah.
Yeah, okay. So you start with the left-hand side
Mm-hmm.
of 922, yeah.
Mm-hmm.
And then,
I switched it, and then I manipulated it to have not P and the universal quantification.
yeah,
And so I was wondering if I could use 917 again to switch
sure,
it back.
yeah.
Even though the P's out front, that doesn't matter.
Oh, wait.
Because she has.
Wait. Yeah, hold on. You got to be consistent. You're saying 917?
Mm-hmm.
Well, you got to be, it's got to be, well, you've got to be consistent. I mean, if you're going to use 917, then if you have, you got to have a P here and a not P here, right? Or if you could use 9.18b if you have a not P here and then a not there exists. I guess I don't understand your question. Tell me what it is that you, tell me what you have at one particular step.
I have not, parentheses, P and,
Oh, you have not outside of parentheses.
yeah, well, I used De Morgan's to get outside. And then I have
P and what?
quantify of all,
Okay, we say for all x, range what?
range true,
Range true,
body not R.
not r. And what do you want to do, what step do you want to do from here?
I want to use 917 to make it,
Okay, so you're saying equals by 917. This would equal by 917. Now, in 917, we're going to substitute equals for equals, right? So this would be not P and then whatever this substitute equals for equals with 917. Oh, but the trouble is, this 917 has a, it would be, you should, yeah, you should have a not P here. You should use 918b, right? Are you with me? Are you with me? Here you would use 9.18b, I think, because 918b has a for all x range r body not p. So it'd be 918b with r replaced true. Oh, with actually with rp with
with RP.
rp replaced true not r. Are you with me?
No, just true, just R.
Yeah, just darn.
Oh, sorry, just, oh, you're right, because the not's there, yeah. True R. Okay, so I think that's how you, that's what you could do.
Okay. I just don't know what I would do from there though.
Well, I don't either. I mean, because what are you trying to get this?
It has to be P and their
Oh, but a not inside of the whole thing makes it or. Oh, shoot, well then, that's the problem.
How do you get a not out of the body?
Yeah, I don't know, are you sure this is correct? Are we sure that this is,
Yeah.
the way you got to
I
here
I
is?
can go back up another step too. I just used De Morgan's to get the knot on the outside.
Okay, has anyone else done, we're trying to prove 922. Has anyone else done this?
It might be easier to start from the right side.
What you did to Morgan's?
No, I think it'd be easier to start from the left side. Because I think what you should do is you should start from the left side and use one of the tradings and then get,
Trading or generalized Morgan?
sorry, a generalized De Morgan. Yeah, a generalized De Morgan. I would use,
Yeah, so it'd be 4. That's why you're doing it. That's what it is.
No, I mean I have that, but I need to get it to the end.
So she pulled De Morgan's out.
Okay.
Again.
well, I mean,
She did the real De Morgan, like from back in the
oh, the regular De Morgan, not the generalized De Morgan.
no, like from back in the day.
Yeah. Well, exists in X
You
for,
did Morgan on .22.
She used generalized De Morgan and then did De Morgan.
Well, it should be not P or for all X range true, not R.
No, there's a knot in front of the all X because of 917.
Yeah, well, if you want to put that in
well, I mean, it's not a matter of if you want to put it in. I mean, you have to do what it says to do. I mean, so, but I would still think that you should start with the left-hand side. There exists an X range R body P, and then use 917 generalized De Morgan. So what does that say? Not for all X range R body not P, and then use the corresponding,
I used 9.6.
what was it?
I used 9.6.
9.6 looks right. Yes, because that's what corresponds to it. So so what you can do is you pull out the body and you OR it, and then it's that with not the range, right? So it's that, and then you pull out the body, so it's not P or.
Why not P?
Because there's a not P.
It is a not P.
Oh,
When you
sorry.
Pull it out, it's a not P.
Yeah, and then it's, well, it's not the whole thing. Yeah, and so you are right. So it's not the whole thing, and then what you pull out is the P or,
Well, you have a P and.
no, it's P or, right? When you use,
Why do you have not the whole thing?
that's this not.
That's the, okay.
Are you with me?
Yep.
Is everybody clear on that? It's not the whole thing, yeah?
And having that not. Okay.
And I think having that not is what flips
lets
it,
you flip it,
that lets you
yeah.
use the old De Morgan and flips it to and the double negation, and it
Yeah.
works.
So you have not, and then you have not P.
Yeah, I think maybe where you went wrong here was
forgot that not.
No,
was
I
how
have
you or how you hand.
It on the wrong side. Is the issue. I have it on the wrong part.
Give it on the P.
Well, it should be not the whole thing, right?
Yeah.
So maybe, yeah. Oh, okay. So I think we got that one. Are we good? All right. Well, if there's no more questions about the homework, then last time I gave you an example of what I want to talk about today is this exchange, interchange. Well, we were talking about the interchange of quantification, and I gave you an example last time, and I wanted to just give you one more example, similar example, and this is a counter example. Counter example for, so this is a counter example for all y, range q, body, there exists an x range R, body P, implies there exists an X, range R, body for all Y, range Q, body P. Now look, you guys.
That's not, there.
Yeah, it's the other way around, right?
Right.
So what this says is that if it's true that there exists an X, range R, in other words, let me see, what was the example that we had last time? If it's true that there exists somebody who loves everybody, then everybody is loved by somebody. But it's not true the other way around. I want the counterexample. So here, so let's say we have the same P, R, and Q as before. Same P, R, and Q as before. But now suppose it looks like this. So here's the R, and here's the Q, and R is still A, B, and C, and Q is still D, E, F, G, H. D, E, F, G, and H. But now let's suppose that the,
Gale,
yeah, oh, you have a name.
Dolores.
Okay, so A and E is like this, B is like from here, and then to G, and then to H, and C is to F and to H. All right? So let's suppose that it's like this. So A loves D, E, B loves E, F, and G, and C loves F and H. So now, is this true? For all Y, range Q, there exists an X, range R, body P. Is this true? Is it true that for all of these people, there exists an X such that
What is P?
P is loves X, Y?
Yeah. Yes, it is true.
Okay, so this is true. In other words, somebody is loved, everybody in Y is loved by somebody in X.
Sorry, antecedent is true.
Yeah, so everyone in Q is loved by someone in R. Everyone in Q is loved by someone in R. Okay? Okay? But what about this? There exists an X, range R, body for all Y, range Q. P. What is this? Does somebody love everyone?
No.
It's false. Okay, so that's a counterexample. So true implies false, you know. Okay, nope. Right? So it doesn't work the other way around. Now, what I want to do now is, and this is a really important concept, this getting straight how, this existential and universal and what it means to have them nested these two different ways. And so it's really kind of an important theorem. But unfortunately, this theorem happens to be very difficult to prove for general Q and general R. Okay? It's really hard, actually. And so what we're going to do is we're not going to attempt that. So what I do want to do is I do want us to prove it in the special case where Q and R are both true. In other words, are you with me? So we're going to prove 9.29 in the special case of R equivals true and Q equivals true.
Now, if A is an element of R, can it be an element of Q?
Well, it could in general, but in this particular example, it doesn't.
Can R be a subset of Q?
It could in general, but in this example, it's not.
I'm just curious.
Okay, so let's do a proof. So here's what we'll do. We'll go around the room. That's kind of tricky, so put on your caps, thinking caps. Proof, okay, so proof of 9.29 in the special case.
Is this going to be on the test?
It could be. In the special case of R equivales true and Q equivales true. So these are all going to be, all of these are going to be range trues, right? Now, what we're going to do is we're going to start with the whole thing. This is one of those deals where we'll start with the whole thing and we'll get it to true. So let me just write it all out. There exists an X, range true, for all Y, range true, body P, implies for all Y, range true, there exists an X, range true, body P. Now, you have your equation sheets. Who wants to go first? I'll give you the hint. 3.57, 3.57, it's, and you'd never, how would you ever know to do this? This is, yeah, this is P implies Q. This is P implies Q equivales, what is it?
P or Q equals
P or Q equivales Q. So it's this implies this is what? This, it's this or this. Okay, so what is it?
for all Y, range true, body P.
I thought it was
Oh,
there
okay,
exists.
yeah, okay.
Okay, so there exists an X,
Range true.
range true, body
For all Y.
for all Y,
Body P.
range true, body P.
Or
Or
for all Y, range true,
for all Y, range true,
body for there exists an X.
exists an X, range true, body P.
Equals
Equivales
for all Y, range true, body there exists an X, range true, body.
for all range true, there exists an X, body true, range P, boom, boom, right? It's kind of nasty, but doable. I mean, we're following this, right? Phew. Now, why did we do this?
You missed the parentheses at the end.
I am? Really?
No.
I think this goes with this and this goes with this.
Yeah.
And this is, and these are self-contained here and here. Are we good?
Alright. Yeah, you're good. No, you're fine.
Okay.
Okay.
Now, boy, are you ready for this? This equals by
The Morgan.
9.5.
Oh, don't do it. No, don't do it.
Now, what does 9.5, this is wicked. What does 9.5 say? It says P or, and then it has this universal quantification, right?
So we can take
And so we can take this entire thing or this
make it or.
and make it, and put it into the body. Now, why would we want to do that?
So we can have four
Be-
quantifications in one thing.
Well, I mean, because we have an exist here, and then we will have an or there exists here. Are you with me? Are you with me? See, because look, we're looking ahead. Because what we'll do is when this goes into here, we'll have an exists or there exists. And what's the operator for or? Sorry, I just...
There it goes.
What's the operator for exists? Or.
So can we use one of those?
And we can use one of those generalized. Right. But we got to get it in there. Okay, so what is this? Now, does everybody understand? This whole thing is going into here. Are you with me? So what is it? So what do we have?
For all y, range true, body.
Yeah, it's this for all y. Yes.
Yeah.
For all y, range true, body what?
There exists an x,
Exists in x,
range true.
range true, body.
For all y,
For all y,
range true, body. P.
range true, body p.
Or,
Paren. Are we good on the parens now?
yep,
And then or what?
there exists an x, range true, body. P.
Or there exists an x, range true, body p. Oh my goodness. And are the parens right now? This paren matches this one. And that whole, we still got to bring this down. Equivales for all y, range true, exists an x, range true, body p. Are we good?
Yes, we have a good roadmap.
And what did we just get through saying that we were going to do?
Use one of the general.
Yeah, which one? Can you tell me, can you point out in your, can you discover in your equation sheet which one?
P or something.
Which one will allow us to combine, wait, it's this there exists and this, we have this exists and this exists with an or, right?
It's a range split. No.
No, we're not in a range,
How about distributivity? 815.
that's a good call. Equals by 8.15 distributivity. Because where star is what?
Existential / or. This is the same thing.
Yeah. Star is the or operation, right? Because this exists, right? Is everybody good? Okay, so what would this be?
There exists an x.
Well, we still have to bring this down,
Oh, right.
right? All right, is everybody good that we're working in the body here?
Yeah.
Yeah? Okay, so what would this be? For all y, good. Range true, body. There exists an x, range true. But now what is our body? Okay. Now, where are we here? we're inside. So there exists. So this there exists an x, and this there exists an x with an or. So what do we have?
For all y.
For all y, range true, body p.
For all y, range true, body p
Or p.
or p. Is everybody with me? Is that now? This is very nested. Yeah.
Very nested.
Are we good? So this is for all y, range true body p or p. Yeah?
Equivales, blah, blah, blah.
Equivales for all y, range true. There exists an x, range true body p. Yeah? Who? Now comes some magic.
You don't do magic.
Yeah, we do magic. Nothing up this sleeve, nothing up this sleeve, nothing up this sleeve. I will now create jobs for the economy. It's going to take some magic. Okay, sorry for that political aside, economic, political. Okay, anyway, do you remember what a lemma is?
A lemma.
Yeah. Okay, so I'm going to pull a lemma out of the hat. I'm going to claim this lemma. For all y, range true, body p, or p, I'm going to claim that that equivales p. Which, that happens to be this. Are you with me?
Yeah.
That just happens to be this. Now,
Now we have to prove that.
we'll have to prove that later. We'll have to, after we finish this proof, then we'll say, okay, prove the lemma. But take my word for it. We'll do this in a minute. Are you with me? Yeah, and so if we do this, what do we have? Good observation. So what would, if this lemma is true, what do we have? For all y, range true, body, there exists an x, body p, equivals for all y, range true, body, there exists an x, range true, body p,
3.5.
which is 3.5, which is 3.5 reflexivity.
With P replaced by.
Yeah, with p replaced by for all y, the range true, there exists an x, range, blah, blah, blah.
Ah.
Anyway, this is equal.
Look at that, and that you need to do something like a lemma with it.
Yeah,
Experience with it? Okay.
but yeah. See, what has happened is with this system, people have, the people who came up with the axioms, they had to work through all of this, and it took them a while. Yeah. So some of these proofs are obvious, but some of them are not. And yeah,
A
question?
lot of our theorems that like don't have any names by them or anything,
Uh-huh.
pretty much like probably originated as lemmas, right?
Maybe so. Yeah. I mean, actually, that's a good point. What you call a lemma. Yeah. What you call a lemma is kind of arbitrary. I mean, a lemma is really just a theorem. It's a small theorem that you use to prove another theorem. But this could very easily have been on the equation sheet as a theorem, And then we would have just said by theorem, whatever, But it would have had to have been proved before this.
Yeah, I mean, all the proofs that you used before, those could all be limits. If you really rigorously, we're using this proof to get to this step. Well, how do you know that
Yeah, it's by, yeah.
You have to prove that.
Yeah. In fact, I actually did a project with an undergraduate. We used this system to devise a set of axioms and theorems for temporal logic. And we had to go through this. Well, should this be an axiom or should this be a theorem? You have to decide all that stuff, So we are using what Gries and Schneider have given us. But in some sense, in some systems, like there would be some things that you would call. There's choice. Some things that in one system would be an axiom would be a theorem in another one, but you'd have a different axiom. And so the question is, how do you choose your axioms in a meaningful way? And so there's some flexibility. But the main thing is, all deductive systems are based on axioms which are not proved. That's a key idea of deduction. So let's prove the lemma.
Now when proving a lemma, can you still only use the previous, like the same theorems we would use to prove this one?
Yeah, we shouldn't use anything after 9.29. We can't use 9.29 and anything later. As long as we use what went before that, then we're okay. So I'm going to start with the whole thing. For all y range true, body P, or P equivals P. Whew. Well, this looks a little familiar, doesn't it? Does this look a little familiar? Something or P equivals P?
Oh, no, go back to that
No.
application one.
Something or P equivals P? Isn't that one of our implies?
Something implies.
Isn't that one of our implies thing? We had 3 implies. We had our old friend 3.5, 3.59.
It's 3.57.
Oh. So what does this equal by 3.57?
All y range true, body P implies P.
For all y range true, body P implies P. Now, do you believe this? Property of textual substitution. Do you believe this?
What?
pulling a rabbit, really pulling a rabbit. Remember how I said nothing up this sleeve, nothing up? Here's a rabbit. For all y, range true body P implies P. Now, do you believe this, that if there's any y, for every y that's in P, what if every y that's in here, what if I replace it by y?
Then it's still P.
Then it's still P. Are you with me?
Okay. Keep going. I'm curious.
Now you tell me. Now you tell me.
Instantiation.
So that way you can go.
Wait. Which is, but now what do we have here?
Instantiation.
Yeah, which is instantiation.
What?
9.13.
Cheater.
Which is
Cheater.
9.13 instantiation. With what?
Cheater. X replaced by Y. And E replaced by Y.
Yeah, which is instantiation. With XE replaced by YY. Boom. We're done.
I don't know how I feel about that.
Yeah. I know, that's, it's,
Doesn't this whole thing of lemmas kind of introduce a loophole to this entire?
no, it doesn't introduce a loophole as long, okay, let me ask you this. What I could have done, and perhaps it would be more comfortable for you, or sometimes what is done is you prove the lemma first.
Sure.
All right. So maybe if I had started over here and proved the lemma first, then I could say, okay, this is a lemma that we're going to use, and then we could come over here and say lemma. But do you agree that I could have proved this first and not used anything? I mean,
Sure.
so
Could we have like cut and pasted that proof and just put it in there?
exactly, yeah, you exactly could do that.
Okay.
You could exactly, what he said was, could you just take this whole thing and put this all inside this step? And you could, but see, you'd have to carry, yeah, and furthermore, you'd have to carry all this other stuff along with it. Every time you'd have to copy that down.
All right.
So, I mean, that would be really ugly, right?
Right.
So lemmas are really a way to, not have to do that. But logically, that's absolutely correct. That is absolutely correct. As a matter of fact, guess what?
What?
Every proof could be done with only axioms. And what you could do is, whenever you needed to do a theorem, you could just prove that within that, and then always get it back to an axiom. I mean, so.
What happens if we stumble upon a lemma that is something that, that is a theorem that we're not supposed to use yet?
What do you mean, stumble upon it?
I don't know, if we decide that we want to try and prove this just to see if we can.
Oh, yeah. Actually, I've actually seen that happen before. A person would go and try to prove something, and then in the proof, the person would take like a part of that proof and do in 3 or 4 steps, get that to something else, and then go ahead and that something else that he proved was a theorem that came later.
Right.
But because it was within the proof, it was legal.
Okay.
Are you with me?
Yeah.
Because those were steps. He didn't use this later thing.
Make that
But
use previous steps that we were able to use.
Yeah. He did like a little sub-proof, he would do a little, you could do, and that can happen, and there's no objection to it, right? I mean, how can you object? He used everything that went before, right? So you can't say, oh, well, but this is a proof of something that came later. Well, I know, but you didn't use that. You did the proof within the other proof, and yeah. But as long as everybody, see, this is a really good illustration of the structure of what a logical deductive system is. You always, and any logical argument that you always have axioms that are not proved, that have to be assumed. So even when you have English arguments and you're arguing with some point, does Superman exist? Whatever, you always have that characteristic. Okay, good deal. Well, it sounds like you guys are really with me here. So this sounds good. All right. Now, I actually think that the next thing that we need to do is we need to talk about English.
Horrible language.
Yeah, English is a horrible language now, you think, huh? Yeah, it's too bad we can't just speak to each other in formal methods, huh? Does there exist someone who wants to go to a party tonight? And of all the Okay, so tell me again.
English is bad language.
No. What is a predicate?
It's a function.
Function that gives a Boolean.
It's a function that returns type Boolean. And what is a proposition?
Statement of true or false.
A declarative statement that's true or false. So the key thing with a predicate is that it's a function. And even though it returns type Boolean, what about its arguments? They don't have to be Boolean. Okay, they could be, but they don't have to
Could
be.
be English.
All right, so predicate, function that returns type Boolean.
So loves X, Y is a predicate.
Mm-hmm. Because the type of the argument is a person, but it returns true or false depending on if X loves Y. So a function that returns type Boolean. So here, let me give you an example. Actually, what we need to do now is we need to learn, there are some really common predicates in mathematics that we need to learn and know how to express them in formal methods. So the first example that we're going to use is mult. Mult nx is true when n is a multiple of x. Is true when n is a multiple of x. And let me give you an example. Mult, a few examples. Mult 27, 9. What is this? What is this? What does this equivalent?
True.
True. Okay. And what about mult 15, 4? That equivalents false, because 15 is not a multiple 4. And what about mult 624?
False. It's a factor.
Yeah, this is also false because 6 is not a multiple of 24. The multiples of 24 are 0, 24, 48,
Well, yeah.
right? Okay, so this is false. Is everybody with me on this? Now, so everybody kind of understands what this means kind of informally, right? Now let's formally define what mult is. The formal definition of mult. Formal definition of mult. Here it is. Mult n z equivales. Now, do you think, I give you a choice here. Is it going to be universal or existential? Why is mult 27, 9 true? Why is that? Is it because there exists something, or is it because for all something?
Exists.
What exists?
There exists an n.
There exists an n that
Well, no,
can
no,
be
no, no,
multiplied
to-
by 9.
Yeah, wait, but this is n. So,
There exists another number like
There exists a,
okay, so let's say there exists an m.
Sure.
There exists an m type what? Let's annotate it with a type. What type? What does m have to be?
Positive integer. Any integer. A z.
Yeah, an integer. Okay? There exists an m, some integer m,
Range true
range true,
out of everything
such that what?
so that z times m equals n.
Only these are numbers. So it would be equals, not equivals.
Equals.
Are you with me?
Yes.
Okay, so such that n equals m times z. Now, does everybody, this is really important that you understand how this works. Why is 29 a multiple of 9? Because what exists? Because 3 exists. Are you with me? That's why. 27 is a multiple of 9 because 3 exists. Are you with me? That's what multiple means, okay? Now, how about, let's do another one. Now, I think we've used this next one in an example or two.
Love.
No. Even dot x is true when what? Yeah, when x is an even number, okay? So, what do we have? So, even dot 5 equivals what? False. Even dot 6 equivals true. So that's a predicate. Even though this says type integer, even returns a Boolean. So what is the formal definition of even?
Oh. I had to do this before.
The formal definition of even is even dot x equivals what?
I think it's a for all.
For all,
Oh, do you think it's a for all?
Well, I mean,
No.
you can exclude all the odds just by putting something in the body.
Hmm?
There exists a z,
Let's call it k.
k, that is of z,
That is type integer.
range true.
Range true. So why does even dot 6 equival true? Because what exists?
Because 2 exists. Because 6
No.
divided by
It's
2
3.
is 3.
Well, we don't have a concept of
Even-
divided by.
Okay, an even number has to be divided by something that gets it to be 2, right?
So it was multiple.
Yeah, I'm right. I'm right.
Mod? No, we don't have a concept of mod. Using only addition, subtraction,
I'm right.
or multiplication. Or addition, using only, yeah, I'm sorry, using only addition or multiplication. Say that those are the two operations that we know how to do.
Division?
No.
Oh, okay, gotcha. So, because k
Why
times
does it have to be multiplication?
k times 2 equals x.
Yeah, there exists a k such that, yeah, exactly, such that 2 times k equals x. Are you with me?
As long as k is an integer and not a decimal.
As long as k is an integer.
Yeah.
That's why we say k is an integer, right? So why is even dot 6 true? Because what exists? Because 3 exists. How about even dot 24?
It's 12.
Because 12 even dot 24 is true because 12 exists. Are you with me? Does everybody understand this? Okay, so that's good. All right. It's time, I see by the old clock on the wall, for us to call it quits. So see you next time.
By the clock or by the light, Jason?